Buckle up, children. We're doing a big boy problem today. We're doing n queens. The n queens puzzle is the problem of placing n queens on an n by n chessboard such that no two queens can attack each other. Given an integer n, return all distinct solutions to the n queens puzzle. You may return the answer in any order. Each solution contains a distinct configuration of the n queens placement, where q and dot characters both indicate a queen and an empty space respectively. So for example, if you have a n equals 4 board, it looks like there are two, so this is the solution of n equals 4. It's not necessarily the only solution. No, I take that back. There are two distinct solutions. That's it. This is all of them. This is every possible solution for n equals 4. So you've got, see, each queen has nothing diagonally in the same row or the same column. So you can take this as kind of a suggestion that there would obviously be no more than, you can go, I'll just show you. The solution is going to go row-wise. It's backtracking. A problem like this, if you're ever asked this in an interview, it's only going to be because you probably nailed the first question, and this is just a follow-up to kill time with the rest of the interview and see how far you get. I don't think you'd be expected to fully finish a problem like this. It would be more a game of, can you get at least as far as the next candidate over? Can you? It's just a game of doing better than the others. It's not about actually finishing the problem. So I'm gonna do, in this main function here, I'm going to just set things up and then call the functions that do actual work, and those are going to be recursive. So I'm going to set up the output on the broader scope so that it's just kind of called from all the others. That wouldn't be something you could do easily with, say, a multi-threaded implementation, but we're not doing that here. It's just to get it right. So it's got to return a vector of strings. So for example, a string, it's gonna be a single row, and a vector of that is a 2D board, and a vector of all that is a list of every solution possible. I'm gonna call it ret for return. So what this main function is gonna do, it's going to, let's define like our first empty board. So that'd be a vector of string, and it's called board, and it's got n rows, and each row we're going to initialize with a string, and that string is going to be n columns long of the dot character. That is how we are initializing our 2D board. So it's a vector first, that, n rows, string, n columns of dot initialized. All right, what do we do next? I'm gonna call my main function, not main, it's the one that does the actual work. It's called solve. It's gonna take a board, and I'm gonna have the solve function just take a row, and then it's gonna return the output. All right, now that that's set up, what does this solve function do? This is our main backtracking. Yeah, it's the backtracking function that does all the work. So it's gotta do something. There's gonna be a main. Okay, I should define the function signature first. It's gonna return void because we have this here, and it's just gonna reference this instead of trying to mess with like passing the total solution across a bunch of call stacks. So void solve, it's gonna take a vector of string called board, and it's gonna take an integer. No, see, I'm gonna call it r for row. And then there's a reason I'm not referencing this by, I need to think about it. I may decide I want to, I'm gonna try with this ampersand here and doing it by reference, but I don't think that would be wise. I'll try it. but I think it would be better to pass it by value instead, and I'll show you later on. So we're gonna have a main loop. It's gonna for int row, so column equals 0 to the size of the board. Column is less than board dot size, and the board dot size, the rows and columns are the same, so that's fine. It's just up to n. But since I don't have n defined here, that would be the way to do it. So what is it going to do? It's going to check something. If, and I'm going to use a helper function called isSafe. And I'll define it after this. But what this helper function is going to do is going to say, if we put a queen in a particular spot, so this particular spot at this row and this column, would that result in a queen being able to attack other queens? Amber alert! It's going to result in, it's going to check, and since we're going down by column, we're going to assume that there's no queens below, because we haven't gotten there yet, below or to the right. So it only really needs to check above. It might need to check to the right too. I got to think about that. So if is safe, board, row, column. If that position is safe, then we're going to do the actual backtracking. So what does the backtracking do? We're going to set the board position, row and column equals Q for queen. We're going to put a queen there. We're going to call solve on the next. So we're already going to call this loop already handles calling it on the next column. So we want to call it on the next row. Solve board row plus 1. Yeah, just on the next row, and then it will have a loop that'll calls on the next column. So maybe if we're okay, so if we start here, we would go on the next row. The next call of it could potentially go further along in its for loop, and actually I think it will go all further along in its for loop before the current call stack does. So actually I think we do need to, yeah, isSafe is going to need to check to the right as well as to the left diagonally. And then, okay, so after we return from our recursive call, we're going to return not return, but we're going to reset this value. We're going to take the queen away again. And we're going to say, okay, if we didn't put a queen there and we continued on, what would we do? And this is what makes the runtime pretty nasty. So backtracking in general is going to be exponential. It's just horrible. It's not optimal, but it's very thorough. It is NP hard. It is not polynomial, no way, shape, or form. It is very, very slow. That might be all that solve does. I gotta think about that. Let's define isSafe. It's gonna return a Boolean. And it's gonna take a vector of string. It's not gonna modify board, so it's definitely gonna take that by reference to save a little bit of memory. And then integer row, integer column. What are our conditions? There are, let's see. It's gonna have to do, it's gonna do another, there's gonna be another for loop. Another for loop. This isn't super fast either. Integer I equals 0. I is less than board.size. And then we increment it. We can get away with one loop though by killing a couple of things. So at most, the length of the diagonal and the length of a vertical will be the same. So for example, here you might go 3 up, and then there you might go 2. It looks like 2 over. What I'm going to do is just we're going to go the maximum amount, which is the size of the board, and there's going to be 3 conditions. There's going to be the vertical, if there's a queen in the vertical, if there's a queen on the diagonal to the right and if there's a queen on the diagonal to the left. So I'm going to check 3 conditions using this one loop up to the length away. So the first one, let's do the vertical first. So if I'm going to make sure the queen is in bounds, the loop I think takes care of out of bounds elements, so we only need to check if it's in bounds. So if let's see, if I minus rho, no, if rho minus I, so if it's up to I rows above, if it's greater than or equal to 0, so it's in bounds, and same with the column. So if the column, would it need to? Oh, you know what? This solve is recursive, so there needs to be a base case. While I'm thinking about it, I'm jumping around, but yeah, recursive functions always need a base case so that they don't, recurse forever. So what is our base case going to be? If the row is equal to if it's the maximum size of the board. So if it's board dot size, meaning we've already covered we're one. So if the row so board size is 4, if we're down here, then yeah. So row board dot size, we want to certainly return, and I think we want to, if we've gotten all the way down, that means, so for example, for board size of 4, if we've gotten all the way down here, that means we place as many queens as we're going to, however the board is. That would be a solution, I think. I'm trying to think if I need to check anything else, but that might be fine. So ret.pushback board. Yeah, okay. And then let's see. So if this is, assuming this is going to be single threaded, I think, and we're not, so we're going to have one call stack being executed at a time. So I think it's okay to pass the board by reference. That's just something in the back of my mind there. Okay, back to isSafe. So we're checking if it's in bounds and if board call row and column is equal to a queen. So we're scanning the column above and we see a queen, then we return false. All right, so now let's check diagonally to the left. Row, column. Oh, I don't think I need to check the column on this because I'm not adjusting the column. If row, board. All right, let's try this. So now we're checking diagonally. If the row is, all right, row, column, row minus I. That's what I was missing. Row minus I. So now checking if this is in bounds is 0, and the column minus I is in bounds, and the board. Let's check the board position for a queen. Row minus I, column minus I. So diagonally up and to the left. I'm going to align these a bit for readability. That's better. Last condition, diagonally up to the right. If row minus I is in bounds, goodness. and the column plus I. So it's diagonally up to the right, less than the size of the board. So if it's not past this right marker, board.size. And board row minus I, column plus I. Checking for a queen. Then we return false. Now we've got our three conditions. If none of those are true, we're going to return true for it's safe to put a queen in the proposed position. That is our helper function. Let's see. I'm going to scan back over and see if I missed anything. Board, and then we're going to call it on the first row, and then we return. In the solve function, we've got our base case, where if we hit the end row, it's not possible to add any more queens. So we're going to go ahead and add it to our solution and return. What would we do then? So if it's not the final row, then we're going to scan from left to right and check every possible column and do a recursive call. So if the board, if it's safe in this particular position, so if it's not safe, we would keep going through the loop, and we only ever call solve again when it is safe to put a queen somewhere. So for example, here we call it again on this. So we put a queen there. Let's see. Yeah, maybe worth stepping through an example. I wasn't planning to step through an example, but I might go part way through one. So the first time it's going to call solve on here, and that's going to go through this row, and it's going to call solve. It's going to call solve again here. So it's going to try queen here and here. And then it's going to do it here again. And it's going to not be able to place a queen here. It's going to not be able to place a queen here or here or here. So it's never going to get to this bottom row. So it's never going to call solve again in this middle row or this bottom row, and it's never going to get to here where it would actually add a solution to the board, to the final output. So that makes sense. Okay, so then the next iteration of the outermost loop, it would try to put a queen here, and then it would go to the next row. It would try to put a queen here. It can't. It can't. It can't. It would put a queen here, so then it would call solve again on the next row, and then it would put a queen here because it can. So it's gonna scan. Let's do an example of the isSafe function. So for checking this position here, int I equals 0. Actually, I'll do. So let's do isSafe from here. After we've already, no, it would never try to put a queen there if it made it there. I'll do isSafe on this position. I'm jumping around, but suppose we made it all the way to this position here, so it's called isSafe on here and here and here, and then it wasn't able to call isSafe here. It's calling isSafe right here to see if it can recurse. So what does it do? We've got the board, and it's gonna go I from 0 to n. So the first condition, if r minus 0 is greater than 0, it is, and the board r minus 0 and the current column, so just this current position is a queen, return false. That is not true, so we're going to do the next condition. All three of those are going to check this same position first, so then let's do the next iteration where I is 1. So row above is greater than 0, it is. That is not a queen, so that's not gonna trigger. And now diagonally above, so r minus I and column minus I, those are both greater than 0. And board r minus I, that is gonna be equal to a queen, so we're gonna return false, so it's not safe. All right, so that's the queen that triggers isSafe from here. So yeah, it's gonna look in concentric circles. So here, and then it's gonna check these, this. It's gonna check this, then this, and then if none of those have queens, it's gonna check this, then this, then this. So suppose there wasn't a queen here, it would check here, then here, and then here, and oh, that's a queen. So then it would return false again. So hopefully that covers it. It might be. Do I want to try to talk about runtime? It's it's exponential. I don't know how much detail that actually wants you to go into, but since for every single position you're doing an n by n loop basically. So for here you're doing this for loop, this outer for loop, and then for each element iteration of that for loop, you're doing a recursive call potentially down there, and for each one of those recursive calls, you're doing another for loop, and then another recursive call. So let's say it wasn't recursive. So this alone, this for loop, and then this, that would be n squared, where n is the one size of the board. So I guess technically the board isn't an input, only the value n. So even if since n is a value, that means that the runtime can really only be pseudo-polynomial, not actually polynomial. Since it wouldn't be a size of an input, it would be a value of input. And then that gets to be having to do with like, then you start basing runtime on the number of bits used to represent n, and that gets pretty messy too. So the number of bits used to represent n is logarithmic on the value of n. And yeah, so each one of those recursive calls, you do another n by n. You could potentially do a recursive call on every single space. You certainly do at least 4 of them, but probably more. And for each one of those, so it'd be n squared times n squared. It's for each n squared, you're doing another n squared operation. So like n squared to the n squared. It's something messy like that. I don't know that it's even a good idea to write down because it's so slow. I'm gonna give it a run for syntax. Compile error. What I miss? Undeclared I. Oh, because I messed up the variable. C. It's a C, not an I. So let's try that again. Accepted. All right. I think it's been enough time on this problem. So the key to backtracking is generally that there's a lot of recursion going on, and say before doing it, you'd set whatever. So you've got some partial solution, you set a value in it, you call your recursion to see it, and then that's going to continue on to like the rest of the problem. So you'd recurse on like the next row down, and then when that returns, you're going to undo your change to the partial solution and continue on. That's what makes it backtracking. And every time you hit this, base case at the very end of it, if it makes it that far, that's when you add your output to the result. So yeah, this is the key to backtracking, this part right here. And the rest is all kind of problem specific, not sugary, but this is all very problem specific. This is specific to n queens. This is the heart of the backtracking, is doing some maybe a conditional check, but particularly these 3 lines here. Adding a queen, recursing on the next row, removing the queen when you come back. So the stack kind of takes care of keeping the partial solutions clean. And then the other thing to keep in mind is I had the main function just kind of set things up and then kick off the real functions that have the signatures in the form that I want them. And yeah, I'm going to submit that. Cool. And then we can mark it off. And you guys have a beautiful evening.